All right, with this module, we're going to start talking about something called the reciprocal lattice, which is a part of reciprocal space. So every crystal lattice that we can draw has a corresponding reciprocal lattice. And as you might be able to infer from the name here, we name it that way because many of its properties are reciprocal to those of the crystal lattice. And you might be asking yourself kind of why we do this. Why would we make up something called a reciprocal lattice? Well, it's important to remember that when we talked about an HKL plane, right, we came up with the Miller indices, right? So the Miller indices are reciprocals, right? Of the intercepts. So we are effectively defining the planes by reciprocals. And so that might give you sort of a first clue as why we're trying to do this. And so we are going to look, we are going to talk about reciprocal space. And this is, a made-up kind of space that is reciprocal to the components that we have in normal space. And we do that so we can interpret Miller indices as components of a vector. And those components of a vector will be the H, K, and L, right? So this is kind of why we do it, because of how we constructed the indices of a plane. And so this vector that we're going to talk about from the plane, this vector is useful for a couple reasons. So one, a vector is normal to the HKL plane. So the vector in reciprocal space is normal to the plane in normal space. And secondly, the length of the vector is related to spacing. So the interplanar spacing. So when we construct this vector in reciprocal space that corresponds to a plane in what we call real space, so just space that you're thinking of, the reason we do it is because this vector related to normal, the real space plane, tells us two important features. The vector is going to be normal to the plane in real space, and secondly, the length of that vector is related to spacing of planes, so interplanar spacing that we just talked about for planes in real space. So if we see something reciprocal lattice, it's telling us information about the real planes in normal space. So that's kind of the power of reciprocal space. And I'll try to give you examples as we go through of why we're kind of doing this. All right, so now I want you to kind of think about how the reciprocal lattice works, what we have. So I've got a picture of one here. So we have an origin that you can see here at the middle point here. That's our origin. And then we have a series of points, and you can see that they're in a very periodic array, just like real space points would be. So each one of these reciprocal lattice points corresponds to a set of real space lattice planes, right? Because if I draw a vector from the origin to a given point, that vector, we know from what I just mentioned, is related to a set of planes that are HKL, right? So I can draw a vector from the origin to any given point in this reciprocal space, and that tells me about a plane. So that's why you see each one of these points has indices, and these indices correspond to those HKL planes. So this is an example of a tetragonal crystal and the reciprocal lattice of those. So this is one that's also in your textbook, figure 2.7, but this is what reciprocal lattice might look like, at least one plane of it in reciprocal space. So again, each one of these points, you can form a vector from the origin, and that means that they correspond to the plane. So this first one here, this point, corresponds to the real space plane 1, 0, 0, this one to 2, 0, 0, this one to 2, 1, 0. So again, since the vector is normal to the HKL plane in real space, it gives us an idea of orientation. And the length from the origin to the point, the vector, the length of that vector, is telling us about the spacing between consecutive planes, right? So the length here tells you about spacing. So my length here is different than my length here. That's one indication we have that this isn't cubic, because if this was cubic, this length should be the same as this length, right? Because those distances are the same in real space. So that's one indication that we can tell that this is tetragonal and not cubic. All right, so what I'm going to do is we're going to go back to the paper, and we're going to go over some of the math that's involved with reciprocal space. All right, let's go over some of the math with reciprocal space. And let's start in real space. So I'm always going to make these connections between the two. So in real space, a direction or vector from the origin is represented by a vector. So we call that vector R, and it has indices of u, v, and w, right? So that vector is some length in the A vector plus some length in the B vector plus some length w in the C vector, right? So those vectors, A, B, C, are the basis for the lattice, right? So think X, Y, and Z. So these are basically your Cartesian coordinate vectors, right? But we're going to call them A, B, and C because they, in this case, we're generalizing because they don't have to be normal to each other. All right, and then the components U, V, and W are integers for indexing the direction, right? So that tells us how much length in each given basis we have to reach a given point in space R. All right. So you saw this part before, so this isn't anything new. So now in reciprocal space, we want to define our reciprocal space vectors just like we would have in real space. So we kind of want to have the corollary to A, B, and C. So in reciprocal space, we have an A vector, but we call this star. So the A vector, so A with the arrow means vector, and then the star here means that we're in reciprocal space. So anytime you see the star, that's going to be reciprocal space. So we can define this by its real space components. So it is the B vector cross the C vector over V. And so here here V is the volume of the unit cell. And so we can define this as A vector times dot product, and then cross B and C. So we can also define the volume in terms of our vectors, right? So B cross C and then dot product with A. Right? Okay, and then we can define the rest of the vectors. So B star is C cross A over volume, and the C vector, C star, is A cross B over volume. So they're all over volume, and then just the different cross products in those cases. Right? So this is just our definition for the basic sort of building blocks that corollary to A, B, and C in reciprocal space. So you don't necessarily need to memorize these equations, but I just want you to sort of know where the kind of the definition of reciprocal space in terms of real space comes in to play. So if we want to define a vector in reciprocal space, we can define it with these three bases. So our vector, and we'll call that DHKL vector, and again star to indicate that we have reciprocal space. We can define that as H times the A star vector plus K times the B star vector plus L times the C star vector. So a point in reciprocal space, the vector drawn from the origin to that point is defined in this way, similar to how a point in real space is drawn. But you can see here it's purposeful. You can see that the coordinates, the indices, are H, K, and L, right? So that corresponds back to a real space plane of H, K, L. So this is going to be very important when we look at diffraction studies, because a lot of what we end up seeing is this sort of spot pattern that you saw with the tetragonal reciprocal lattice, is that this is actually produced from diffraction. So we actually kind of see reciprocal space when diffraction occurs. And so that's the importance of the reciprocal space and reciprocal lattice, because that diffraction leads to a reciprocal lattice, which can give us information about the HKL values and the interplanar spacing DHKL. All right, so one thing you should keep in mind when we talk about reciprocal space. We just defined a vector DHKL star, right? Well, this is in reciprocal space. So when we are in reciprocal space, the units are also reciprocal, right? So we think of DHKL as the interplanar spacing, but this is in reciprocal space. So this, the length of this, the absolute value, is actually equal to 1 over the length of DHKL vector in real space, right? So that is 1 over DHKL. So if we have, so what this is telling us is that if we're looking at a spot pattern where we can come up with this DHKL vector, DHKL star, right? This gives us information about the interplanar spacing, but it's the reciprocal, right? So if we want to know about real space, which is going to always be the case, then we have to take the reciprocal to be able to get this, which is what we often want to do. Oh, and I apologize, this shouldn't have the star there. There shouldn't be a vector. This is just the absolute value. So this is just the length DHKL, not the vector. So that's just another thing to keep in mind about the relationship between D star and the length DH scale.